Ross Harvey here from Hibbing High School, Math 626, presenting video solution number 2. So we're going to be doing this in the confines of an informal basic geometry class, lower level 10th grade geometry class. And it's at the end of the chapter that deals with similar triangles. So we've already proven triangles similar by angle, SAS, SSS. We have done many similar triangle scale factor figures, such as two equilateral triangles of 2, 2, 2, 5, 5, 5. The kids understand they're similar because they have the same shape, different sizes. They understand they're in the scale factor of 2 to 5 or 5 to 2. We move on from there to two triangles that look more like this right here. So take two right triangles, one of them being 6, 8, 10, and it's going to be similar to another right triangle that will be 9, 12, and 15. The kids recognize right away that because 6 is to 9 in a 2/3 ratio, 8 is to 12 in a 2/3 ratio, and 10 is to 15 in a 2/3 ratio, that they become similar and there's a scale factor of 2/3. And let's say you didn't know that side length of 12 right there, you could find it out by setting it equal to x and setting yourself up a proportion and solving it that way. So they're really good at doing this. Well, then along comes the triangle proportionality theorem, which completely changes the game and blows their mind a little bit. Triangle proportionality theorem looks like this right here, and it takes a line that's down here, which is parallel. Excuse my drawing, my drawings usually aren't very parallel. And what happens is you have a side that's split A and B, C and D. You also, triangle proportionality theorem says that if these two lines here are parallel to one another, then the sides of the triangle they intersect are cut in proportion. So it says that on your triangle proportionality theorem, that A is to B as C is to D. Pretty nice, and they get to using that a lot. What messes with them later on is when you start talking about two similar triangles, and you come back and you talk about how this length here is E, and this length here is F, and this length here is G, and this length here is H, and then you start looking at those, and it really, really messes them up, because now if you just look at similar triangles, you have from similar triangles that A is to G in the same ratio that C is to H, in the same ratio that E is to F. So we talk a lot about this in a problem solving section. What they do is they as soon as this happens, inevitably they're going to take B and D and start matching it up with E and F. And I try to get them to understand that that's the only thing that doesn't work. But what I really want to start talking about here is how can this be applicable in a real life situation? So there's a lot of real life ones in a problem that I come up with that I've used a couple times, and this year, just last week, I used it a lot more. And I took a ruler stick. It starts at 0 here, it goes to 12 here, it's 1 foot. And I used this example, and if the weather ever cooperates with us, I'm probably going to take them outside and have them measure a flagpole in the parking lot, a height of a fence, a height of the high school that we go to, Hibbing High School, something to that effect. But there's always one of these drawings here where there's a guy standing here like this, and they talk about this eye level, and he has this eye level that looks up to the top of a fence like this, and his eye level goes like this right here, and he's 5 feet tall, so this is 5 feet, and then he holds a ruler stick out here, that's 1, and you have your two similar triangles right here. Well, I want to take this and change it just a little bit. I want to take me from my eye level, and I want to look at the top of a building like this, and I want to hold a ruler stick out there so that the top of the ruler stick goes to the top of the building, and the bottom of the ruler stick goes to the bottom of the building. And you go like this, take that ruler stick right there. That ruler stick is 1 foot long, 12 inches exactly. This is going to be H, the height of the high school. And as long as you do this right here with it, and I have measured this, I measured this in my classroom yesterday with a meter stick. I literally put a meter stick right here at my eye, and I went from my eye out to here. Not a meter stick, it was a meter stick that had inches on it, and this was exactly 2 feet right here. So what I wanted to show them is that instead of me having to draw this line right here and then say, hey, this is going to be 2, this is going to be 1, this is going to be some partial height of the building, And then I can use these two similar triangles right here as long as I go through and measure this distance. And I can do that after the fact as long as I've marked this position with something. I can mark the distance. What I wanted them to see is that this height right here that will go from my eye, this distance from my eye to the building is the same as it would be from right here to the building. So instead of looking at a triangle with sides that are in proportion and that are similar, I want to look at similar triangles and not talk about a side of the triangle, but talk about a height of the triangle here instead. And look at the height of the triangle being in proportion. So what's really neat is that they get this really quickly, that what would be the difference if I used this and this height right here, and this distance of 2 and this distance of whatever it is in the same figure. So if I went and did this, and again, once I knew that when I hold it like this, and this is 2 feet away from my eye level, and I close this eye like this, and I line this up, and I either walk forward or I walk backwards, so that the top of the high school is right here, and the bottom of the high school is right there on my line of sight. And as long as I mark on the ground where I am, I can get this measurement after the fact. Then I can come up to the classroom and I can say, okay, we know this is distance of 2 feet right here. That marker's not showing up very well. We know this distance is a distance of 2 from here to here. This is a distance of 1. This is the height of Hibbing High School that we want to find. All I have to do now is take a measuring tape from the shop class and measure this distance right here. Suppose that distance there was 150 feet. You're probably going to have to stand a ways with just a 1 foot long stick. I could also go like this and I could do this, but I want to do it here because this is, I know it's 2 feet. So if I do this right here, I measure this to be 150 feet, I've got a really easy problem. The kids will come up and find this proportion right now. They will absolutely recognize that the 1 foot vertical height right here will correspond to the H in the same proportion that this distance away from me, 2 feet, and the distance away from me in the high school, 150 feet, will go like that, and very quickly and easily, they're going to come back with the height of the high school is 75 feet. Or flagpole, or fence, or tree, or house across the street that we decide to use. So, weather cooperating, this is what I'm going to take my class outside and do with this. And it really, I love this idea of having to break it down to exactly 2 triangles to any piece of length on the triangle. Because the next thing we're going to add in the near future is that the perimeter of 2 triangles that are similar. The perimeter is also in the scale factor of 2 to 5. So what they end up recognizing is that any measure, any unit of length is always in the same scale factor anywhere on the 2 triangles. And that stems a little bit from this, because you take this one and put it up this way and see what you're looking at. And it's a really neat problem where they don't actually have to have a measurement that's a side of the triangle necessarily. Thank you. Enjoy.